Okay, so in this section, we're going to talk about limits involving infinity, meaning what happens as x approaches infinity, right? Most of the time in Algebra 2, pre-calculus, we are focused on, what happens very close to the origin. Like the farthest we go is x equals -10 or +10, right? But the x-axis extends far past 10. It goes to a million, it goes to a trillion, it goes to infinity and negative infinity. So what happens to a function as that happens? That's a very, very important part of calculus, and it's a very, very important part in analyzing a function and seeing its behavior. Okay? All right. So let's talk about finite limits as x approaches positive or negative infinity. The word finite means a number that can be defined, like 7, like 254. Okay? We know that the symbol infinity does not represent a real number. I can't get into a spaceship, go out somewhere in space, get off the spaceship and say, okay, I've just landed on infinity right now. I don't know where infinity is. It's undefined. It is not a real number. Okay? Whatever number, whatever location you can wrap your head around and you can define as it's that point, that's a finite number. Okay? We use infinity to describe the behavior of a function when the values in its domain or range exceed all finite bounds. So when you're so far out that you can no longer define it, that's infinity. Okay. When we're talking about what happens to a function as we go in the domain towards infinity, one of the things that we happen to come across is a horizontal asymptote. All right. So the horizontal asymptote is defined as a line y equals a number b. All right. And it's a horizontal asymptote if, there should be an if here. All right. It's a horizontal asymptote if the limit of f of x as x approaches infinity is b. So what does that mean? As x approaches infinity, f of x takes on the value, the vertical value of b, then y equals b is an asymptote, horizontal asymptote. Take a look at this example here. We have f of x equal to x over the square root of x squared plus 1. We graph it. This is what it looks like, minus the red lines, right? The red lines are there for us. So take a look. As x approaches infinity, right? So as I'm going farther and farther and farther out to infinity, what y value is that approaching? All right, so you'll notice y will take on a value of 1 here. So the limit as x approaches infinity is 1. Now, what if as x approaches negative infinity? What y value vertically is the graph approaching? -1. Okay? So these were the limits as x approaches infinity and negative infinity. So we say that this graph has two horizontal asymptotes, and they happen at y equals 1 and y equals -1. Never the horizontal asymptote is -1. No, it's a line, needs to have an equation, y equals -1. All right? Yes, you could also write in concise form y is plus or minus 1. That's also totally fine. Okay, so here it says use graphs and tables to find the limit as x approaches infinity of f of x and the limit as x approaches negative infinity of f of x. So why don't we graph that? We have 2x minus 1 on top. Clear. 2x minus 1 on top. And I need parentheses here. And divided by, in parentheses, absolute value. Everybody knows where absolute value is? Yeah. Yay. Absolute value of x minus 3. Okay, zoom 6 because I don't know what my window was in before. Okay. So first of all, it says the limit as x approaches infinity. Okay. Yes. So as x approaches infinity, it means, you know, when we're farthest, as far to the right and to the left as possible. So if I go to my window, and let's say for x max, I go from negative 1,000, that's big enough. It's big enough that you could figure out the intentions of the graph as x gets very large. Enter, or graph. So now it looks like this. Now I don't really care that I can't see what's happening in the middle because all I care about is what's happening at the ends. And so now all I do is press trace and type in 999. And it looks like the y value is about 2, right? So I say for part A, the limit of f of x as x approaches infinity is 2. And then if I type in negative 999, I'm at negative 2. So the limit of f of x as x approaches negative infinity is negative 2. And then C says identify all horizontal asymptotes. So if as x approaches infinity, right, the limit is a finite number, then I get an asymptote there. Okay, and if I have a finite number as x equals negative infinity, then I have an asymptote there. So my asymptotes are y equals plus or minus 2. Okay? Does this make sense?
Well, yeah. It's just because on the bottom, wouldn't it make it 0 if it were negative 3 and 3?
Where is there a 3?
For the equation, on the bottom, if you put a negative 3 and 3 into the x, it would make it 0 on the bottom. What's that? Does that mean that asymptotes are 3 and negative 3?
Oh, the point where the, that's what? That's vertical asymptote. Good. The point where the denominator is 0 is a vertical asymptote. Okay. All right. These properties, remember the properties of limits yesterday that I said I'm not going to sit here and recite them? The same properties of limits as x approaches a number apply to limits as x approaches positive and negative infinity. So we saw one example here in number 27, right? That was this one. If you have a limit of a function and then a limit of another function, the limit of the products of the functions are just the products of the limits. So we get used to this when we use them over and over again. Okay, now look at this. Have we seen this before? The same exact thing? What have we seen before?
0.
The limit as x approaches 0 of that function was what? 1. The limit as x approaches infinity of that function is 0. Remember yesterday I told you this was a famous function? See? It's back. It's got a buddy. It's actually got a buddy. The limit as x approaches infinity of cosine x over x is also 0. I know, it's pretty cool. They're buddies, yeah. They're buddies. Okay.
Have we ever seen them?
No. That's not so famous. Okay.
What about x approaches 0 and
Well, yeah, we'll come to that. Yeah. Okay. So now, take a look at this one. Evaluate each limit, right? And here it says the limit as x approaches infinity. So when x is infinity, look at the numerator there. I have x squared plus 1. So suppose x is like 1,000,000, okay? And then I've got 1,000,000 squared. That's, think about how many zeros that is. That's 12 zeros plus 1. How much of a difference is that 1 going to make? Not much. So in dealing with x approaching infinity, the only terms in a function that matter are the ones with the higher exponents, the highest exponent. So here, when I'm looking for the limit as x approaches infinity, all I need to look at is the term with the highest exponent on top, the term with the highest exponent on the bottom. And when I only use those, then I have the limit. This is the same as the limit as x approaches infinity of x squared over x cubed. This is the limit as x approaches infinity, 1 over x. Now, which is 0. If you have 1 divided by an incredibly large number, it's 0. Think of 1 pizza, and you're dividing it among 1,000,000 people. How much is each going to get? 0. Now, for all intents and purposes, check it out. If I were doing this for myself, and all I want from you guys is you circle, oh, x squared, x cubed, more x's on the bottom, this equals 0. That's it. You don't have to write this. You don't have to write that. Okay? You can if you want. You don't have to. Here, we have the term with the highest exponent, the term with the highest exponent. What happens to the x's? They cancel, but the coefficients remain, and that is the limit. Okay, this one, when you don't have a polynomial function on top. You have an algebraic and a trig function combined. What we're going to do is we're going to separate this. We're going to separate it, and this is going to be the limit as x approaches infinity, 3x over x, plus the limit as x approaches infinity, sine x over x. Okay? And then we do these separately. So look at the first one, highest exponent. How much is that? That's just 3 plus, oh my gosh, look at what we got here. What's this? It's just a 0, so this is 3. Okay? Remember, if you have multiple terms in the numerator, 1 in the denominator gets distributed to each term. Okay, here, this one, there should be a limit here. So limit as x approaches infinity. This is the same as this product property. So this is going to be the limit as x approaches infinity, 1 over x plus 1, times the limit as x approaches infinity, 4x squared minus 1 over x squared. Okay. Now, oh, by the way, okay, the first one, you have a 1 over x, and we are going to say x approaches infinity, right? So imagine x is a very large number, it's 0. I never want to see you write, oh, x is infinity, so that's 1 over infinity, that's 0. No, 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 no. We never write a number divided by infinity. We never write 3 to the power of infinity. No. Okay? No. Okay. So, this becomes 0 plus 1 times, okay, here, right? Take the highest power on top, highest power on the bottom. What are we left with? A 4. So this is just a 4. Isn't that cool? It's so nice and neat and like, you know, just so clean. Yeah. What about the 1? A 0 plus 1 became a 1.
No, there's a
Right, so you only take the highest power. When it's a polynomial equation, Yeah, you only take the highest power. Okay? Okay, so this was when we were letting x's go to infinity. All right, what if x approaches a number, like x approaches 2, but the value goes to infinity, right? Yeah, so that was infinite limits at infinity. This is infinite limits. It's the same words, but different order. Infinite limits as x approaches a. So if as x approaches a number, like as x approaches 2, the value, the y value, the vertical value of the function gets so big that it's bigger than any number we can count, we say the limit as x approaches a is infinity. If, suppose x is approaching 2, and the values vertically get so small, they're like negative trillion, negative whatever, and farther than we can count in the negatives, we say the limit of f of x as x approaches a is negative infinity. Now, it's also correct to say that these limits do not exist. But, as we said yesterday, you have to differentiate between does not exist, meaning it goes to infinity, or does not exist, they go to different values. So let's see how that works here. So use graphs and tables to find the limits here. Okay, so in this case, let's graph this. So we have x over x minus 2. Zoom 6. Remember, we were in this crazy window before. And we're talking about as x approaches 2 from the negative side. And you can see as x approaches 2 from the negative side, this is going to negative infinity. So here we say this is negative infinity or dne. You could also write dne negative infinity. Okay, so here's the thing. You could just say negative infinity, and that's cool. But you can't just say dne. Not cool. Okay? Okay, this is the integer function, the greatest integer function. It's one of my favorite functions, but we never get to cover it anymore. But anyways, so it's in math, number 5. So here's how it looks. Basically, the domain is only integers. When you just graph the integer function, this is how it looks. Yeah, so you have a graph, like when x is 0 to 1, the value is 0. When x is anywhere from 1 to 2, the value is 1. When x is anywhere from 2 to 3, the value is 2. So y values are only integer values. That's cool, but that's not our function. Yeah, yours might be the function. I was just showing you what the integer function is. The greatest integer function. Over x, graph. Yeah, funny little things. So as x approaches 0 from the negative side, now you can also go to table. Let me show you that as well. As x approaches 0 from the negative side, why can't I go up here? Is it just? All right. Let me trace it. So, yeah, so where is it going here? It's going up to positive infinity over there, right? So here, we're going to say positive infinity or dne. Okay. All right, vertical asymptote. Vertical asymptotes happen when as x approaches a, okay, so if this is a, as x approaches a, the graph goes up to infinity or down to negative infinity. That's where you have a vertical asymptote. So do either of these functions have a vertical asymptote?
Yeah.
Which one? Both have a vertical asymptote, because as x approaches a number, the limit is infinity, and it doesn't matter whether it doesn't matter whether it's a one-sided or a two-sided limit. Okay. So here's where we have our infinities, right? So when you have an infinite limit as x approaches a. Okay, so here it says find the vertical asymptote, then describe the behavior to the left and right of each vertical asymptote. Okay, so here's how we find the vertical asymptote. The vertical asymptote is where the denominator of the reduced function equals 0. All right, so here, okay, so if you factor, okay, and you see that nothing cancels, whatever in the denominator does not cancel out, you take that, set it equal to 0, and at x equals -2, you have your vertical asymptote. It's the term in the denominator. Okay? Okay. So then it says what happens on either side of this. All right, so if I graph this, x squared minus 1 over 2x plus 4. All right, look at where -2 is. So now we want to describe the behavior of this. The limit as x approaches -2 from the minus side is -infinity. The limit as x approaches -2 from the positive side is positive infinity. Okay, that is what we mean by behavior. Okay, does this factor? 2x plus 1, x minus 3. None of those cancel. So I have two asymptotes. 2x plus 1 equals 0. X is -1/2. And at x equals 3. So two vertical asymptotes. And you guys, like, you would know what to do, right, for the behavior. I think I'm gonna move on. Correct. Yeah. So you would have to do the limit of f of x as x approaches -1/2 from the minus side. Limit of f of x as x approaches -1/2 from the plus side. And then for the 3's. I know you guys can do that if you look at the graph, right? But like, yeah, but the behavior would be all 4 of those. Cool? Cool. Sometimes what we find helpful is an end behavior model. This is super helpful in areas like physics, for example, where basically you want, okay, if x was extremely large, how does this function behave? You're like, oh, if x is really large, this behaves like a parabola, okay? Or if x was really large, this behaves like an exponential function. So what they do is they model the behavior of a very complicated function by a simpler one that acts virtually in the same way. How do we do this? The right end behavior model, right, is what happens when we look at x approaches infinity. The left-hand behavior model is what happens as x approaches negative infinity. Okay, so look. It says match the function with the graph of its end behavior. Okay, so we want end behavior, that's x approaches infinity. So you know what I do is, if I'm looking at x approaches infinity, I only look at the terms with the higher powers. So here, this will simplify to what? 3x squared. That's all. This will simplify to negative x cubed over 2. Right? Or it's negative half x squared. Should we write it that way? X cubed. This will simplify to negative x squared. So now, of these three, right, which one models number 1, A, B, or C? B. What about 2? A. What about that one? C. Okay. All right. So here, find a power function and behavior model. We're only going to take the higher term. So we say y equals negative 2x squared. Okay. Is this a rational expression? Is there a denominator with a variable in there? No. No horizontal asymptote. Okay? Okay, so, and what about here? Y equals 3, and what's the horizontal asymptote? Horizontal asymptote is y equals 3. It's what that reduces to. Okay? So, if there are a greater, okay, so if there are a greater number of x's, so basically like if the exponent is greater in the numerator, there is no horizontal asymptote. Okay? So this is section 2, and I would like for this homework to be completed by tomorrow. That's Friday the 28th. Yeah? Tomorrow. Yeah? And so then tomorrow I have like a whole bunch of review packets on both section 1 and section 2. So hopefully by the end of tomorrow, you guys will be experts at this.